Hello, I am Pietro Siorpaes, and this is my talk on Pathwise local times and Tanaka Meyer formula for càdlàg paths. This is joint work with Rafał Wachowski, Jan Oboy, and David Cromwell. Consider Ito's formula in the simplest possible setting, so a one-dimensional continuous semi-martingale x and a C2 function f, and you have here the formula. Now, this formula, we consider the fact that x is a semi-martingale, and the definition of semi-martingale and the definition of stochastic integral and the definition of quadratic variation of the semi-martingale, they all defined using convergence probability. So they all depend on the underlying probability measure P, or more precisely on its equivalence class. And sometimes it is desirable to have an Ito's formula which is made of terms that don't actually depend on P. For example, to develop model-independent bounds for option pricings. There's a large literature on this. I cite the name of David Hobson as standing out among the many contributions. So it would be nice to have some type of pathwise version of Ito's formula. Now, this was achieved by Fulmer in '81. His definition was a little complicated, let's say. So 3 years ago, Conte and Chiu proved that there are many equivalent definitions that one can use, and I will use here one of theirs. So given a càdlàg function x, so there's no randomness now, this is just a function of time, and a sequence of partitions pi n of some interval 0t, assume these partitions have mesh that goes to 0, and define the sampled quadratic variation of x along pi n at time t to be the sum of the square jumps of x stopped at time t sampled at the points of the partition. And then we say that x has quadratic variation, pathwise quadratic variation, sampled along that sequence, and we write that x belongs to Q if the sampled quadratic variations converge pointwise to a càdlàg function, which we denote in this way, and of which we assume that its jumps are given by the square of the jumps of x. Now notice that such function is necessarily increasing, so you can decompose it as its jump part and its its continuous part and its jump part, and the jumps are made like this because of our assumption. And notice that although this definition of course doesn't depend on any probabilities, it's applied to a deterministic function, it actually does depend on the sequence of partitions pi n. Both the fact that x has or doesn't have a quadratic variation and what the limiting object the quadratic variation is could a priori depend on this sequence. And then the question is, do they actually really depend on that sequence? And here are two interestingly contrasting results in this regard. So the first, if x is a semi-martingale and pi n are partitions made of stopping times, then for p almost every omega, the pathwise quadratic variation calculated along a subsequence of the original sequence of partitions equals the quadratic variation. So this object is computed like this. You first take x, you evaluate it at omega, you then get a path, and you compute the pathwise quadratic variation along the path. And here instead you take the classical quadratic variation, which is some process, and you evaluate it at omega. And you get the same object in both cases. So this tells you that as long as you consider partitions made of stopping times, you always obtain back the classical quadratic variation, so the limit doesn't really depend on the sequence of partitions as long as they're made of stopping times. Notice, however, this set of omega could a priori depend on the sequence of partitions. Okay. All right. However, on the completely opposite end of the spectrum, here's a weird result if you want. If W is a Brownian motion and A is an arbitrary increasing process starting from 0, there exist refining partitions made of random times such that the limit of the sample quadratic variations of Brownian motion along the sequence is the arbitrary process you started with. This limit is almost surely simultaneously for all t. So if you start with, say, a continuous increasing process, then you can build such partitions such that the sampled quadratic variation of W is your arbitrary increasing process that is continuous. Okay, so essentially, this shows you really need to take partitions made of stopping times, not of random times. Now we have an analogous result for deterministic functions that they oscillate wildly enough, so they need to have infinite 2 variation on every interval, and then you can prove that there is partitions that made this object converge to an arbitrary object. This we did in a paper I did in a paper with Davis and Oboe 3 years ago. Alright, now we finally come to Pathwise Ito formula as given by Fulmer in 81. So given a sequence of partitions pi n that converges to 0, x that has pathwise quadratic variation along that sequence, and a C2 function, we have the usual Ito formula for càdlàg functions, where here this is the continuous part of the pathwise quadratic variation, so this is a Lebesgue-Stieltjes integral. This object here is defined as this absolutely convergent series. It's easy to prove it's absolutely convergent. And finally, this object here is defined as this limit, which, as part of his theorem, Fulmer proved it exists, and then he proved that it satisfies this formula. Okay, so he essentially defines some type of pathwise stochastic integral if you want. However, beware, first, this is really only defined for very special type of integrants, only of this form, and second, it actually really doesn't have any continuity properties, so I don't, you could argue that perhaps it doesn't deserve to be called pathwise stochastic integral. Nonetheless, it has a very pleasing definition and it satisfies this nice property. So it is now natural to ask what happens when f is not continuous. Sorry, the second derivative of f is not continuous. Can one still build a pathwise notion of local time which satisfies a Tanaka Meyer formula, just like in the stochastic setting? And is it then true that given a semi-martingale, for almost every path of the semi-martingale, the pathwise local time coincides with the classical local time, just like it did for the quadratic variation? And the answer to both of these questions is essentially yes. Now, this was studied in a series of papers in the case of continuous X. So first by Wormley, a PhD student of Fulmer back in the 80s, and then 2 recent papers of Perkowski and Cromwell and Davis, Oboe, and myself. And then that's all I'm going to say for continuous case. Now, in the càdlàg case, this was only considered for the first time in the paper that this talk is aiming to advertise. As you might have realized, this has been a very short talk. I'm really not going to discuss in detail the results of that paper. This is what I will mention, that in the paper we give 3 non-equivalent definitions of pathwise local time, and correspondingly 3 different definitions of pathwise stochastic integral, just for some type of integrants. And in each case, we prove that the pathwise local time coincides with the classical local time on almost every path of a semi-martingale. And we prove Tanaka Meyer formula for a Sobolev function f. So the second derivative of f is assumed to be integrable in LQ. We then prove some other properties of this pathwise local time, and most importantly, we give a contribution to stochastic analysis. We show that given a càdlàg semi-martingale x, the normalized number of down crossing converges to the local time. Now this result was already known in some special subcases, so if X was Brownian motion, it was conjectured by Levy and proved by Ito McKean. If X is a continuous semi-martingale, it was proved by El-Karoui. And if X is a semi-martingale with summable jumps, or if you prefer X equals M plus A, where M is a continuous local martingale and A is a càdlàg, not continuous, process of finite variation, then this was proved by Lemieux. And that's it. So I hope you found the talk interesting enough to check out the paper for more details. The paper was recently published in the Electronic Journal of Probability. You can also find it on the archive. Thank you for your attention. Bye-bye.